Today we're going to talk about leading coefficients, and we're going to talk about end behaviors and which quadrant a function should be starting and ending in. And it's very simple. First thing we want to talk about is what is a leading coefficient. So the leading coefficient is the number or the term that's in front of the term with the highest degree. So we talked about degree yesterday. So if you had something like y equals 3x cubed plus 2x squared plus 1, then the degree of the polynomial would be 3, and the leading coefficient here would also be a 3. Now what happens is we want to know whether or not this number in the front is going to be positive or negative, and that's going to help us to graph the function. So for instance, if I asked you to draw a line with positive slope, you would draw something like this, right? Here's your line with positive slope. Now thinking back to the names of quadrants, because you need to know what quadrant you're in. This is Q1, this is Q2, this is Q3, and this is Q4. So if we have a polynomial where the coefficient is positive for an odd degree function, so odd numbers, right? Odd means 1, 3, 5, 7. Those are odd numbers. So the degree, if the degree is odd, so this one, the degree would be like, this would be y equals x, say. It has a positive leading coefficient, that's 1, and the degree is odd, it's also 1. So it will go from quadrant 3 to quadrant 1. Okay? Now, if it had a negative leading coefficient, then it would be going this way, right? This would be a negative leading coefficient. And it's going from quadrant 2 to quadrant 4. So this would be like y equals negative x. So the degree is 1. It has a negative leading coefficient. Okay, so this is your negative leading coefficient, positive leading coefficient. Now, it just so happens that if you change the degree of the function, so let's say we're going to deal with a cubic function now. So if I had a really basic one, let's start with the most basic. So y equals x cubed. What does that look like? Well, it goes like this, right? Like that. So what you need to note here is that when they are the same positive leading coefficients, they will start in Q3 and end in Q1. So it's going, we're reading from left to right. So if this line's going this way, then my cubic function will also start in this quadrant and end in this one. Now conversely, if I said, okay, well, what if I have a negative leading coefficient? So that would be this line here. So if my cubic function, let's just stick with the easiest one here. So let's say I have y equals negative x cubed. So this is a negative leading coefficient. And it could be any number. So it's going to have the same behavior, same end behavior, and it's going to start and end in the same quadrant as a negative line. So here's my negative line. It's going this way, so that means my function's also going to start in this quadrant and end in this quadrant. So this would be y equals negative x cubed. Now that holds true for any shape of cubic function. They don't all look like this. This has a triple root. So if I had a bunch of single root functions, so let's say I had one that goes like this. There's another leading. I would know by looking at this function that it had an odd degree. I know it has 3 roots, so it's a cubic function. And it also is starting in quadrant 2 and ending in quadrant 4. So all you have to do is go, okay, it's negative slope, has a negative leading coefficient. Okay, so that's pretty easy. So let's just write a little note here. So with an odd degree and a negative, let's start with positive because we're positive today, and a positive I'll just put LC, leading coefficient, function begins in, what did we say? Here's positive line, so it's Q3, and ends in Q1. So we can just do ditto, ditto, ditto here, right? With odd degree and a negative leading coefficient. The function begins in, okay, so odd, negative, it's going to start in Q2 and end in Q4. And in Q4. Okay, so that's pretty easy. You only need to remember what a line with positive or negative slope looks like, and all other odd degree functions will start and end in the same quadrants. So we did talk about end behaviors before. So we're going to have, if you're going to be asked what is the end behavior, you're going to say odd and positive as x approaches negative infinity, y approaches, so as I go this way, this is my odd one, odd and positive, so the end behaviors are here, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity, because it's a positive slope line, right? So negative infinity, positive infinity. So odd and negative is going to be the other way, right? So as x approaches negative infinity, y approaches positive infinity. So here we're starting Q2, so it's coming from way up here, it's going that way. And just like a negative sloped line. So as x approaches infinity, y approaches negative infinity. And again, that would be because it's a negative slope, like a negative slope line. Again, all you have to do is remember whether or not you have positive or negative slope. Just think of a line first, and then that will apply to your cubic function. Okay, so now let's talk about what would happen if we have even degree. So even degree, let me quickly sketch here coordinate plane for you. Okay, so now what you want to think about here is a parabola, because that's the most basic even degree function that you know of, right? So, and let's get a pen here. So let's say y equals x squared. Okay, what does it look like? Like this. So this has a positive leading coefficient, and it starts in Q2 and ends in Q1. Right? So we have this. Now it doesn't matter any positive function. So let's say we have a quartic function. So that would be 4 degrees. Fourth degree. So if I had something that went like this, it's just an example for you. So if I had this function, this is 4th degree. How do I know? Well, it has 4 roots, 1, 2, 3, 4. And notice this would be a positive leading coefficient, and it would end in the same quadrants as your basic y equals x squared. So let's say this function is going through, I don't know, let's put some values on this to give you an idea. So have roots, say this is -2, -1, 1, and 2. So that would mean I would have some function with some a value, and then it would be going through a -2, so that would be x plus 2 for my 0, x plus 1 for this one, x minus 1 for that one, and x minus 2 for this root, right? You know how to do that. We'll do a lot more of this when we have to find the equations. So if you expanded all this, I'd have x to the power 4, and here it goes, it's positive leading in each quadrant. Now the same thing happens if I have a parabola that's going this way. So you know this would be like y equals -x squared. then we should just say that this is positive here. So if I had negative x squared, then the whole thing switches direction. So I could have a quartic function. Let's do one that just comes up and touches here this time, like this. Okay, so this would also have a negative leading coefficient. So it would be negative something. Well, we put double roots here, so let's give it a value. So some a value, which I have to determine, just like you did with polynomials before, or quadratics. So I have x plus 2, and it's double root, and this is an x minus 2 with a double root. So something like that. So the point here is not so much that you know how to set these up yet, because we'll discuss that more, but rather that you understand how the graph is going to look and what the end behaviors will be. So all you need to know for the even degree functions is you think of this function here, y equals x squared, and whether or not it's positive or negative. So for this one, if leading coefficient is positive, then you're going to start in Q2 and end in Q1. So that's pretty obvious, right? It's just the same thing like a parabola. And if the leading coefficient is negative, we're going to start in Q3 and end in Q4. Now the end behaviors for these, let's put this over here, end behaviors. So as, let's go even and positive. So an even degree and positive leading coefficient, that's this one. As x approaches negative infinity, y approaches positive infinity, because it's going up, right? And we could put plus or minus here because it happens on the same, on this side, the same direction, right? As x approaches positive infinity, y approaches positive infinity. So even and negative leading coefficient. So as x approaches plus or minus infinity, y is going to approach negative infinity. So all these are all going downward. So they're all approaching negative infinity as x approaches positive or negative infinity. Okay, so that's pretty much talking about the end behaviors. And the last thing we need to talk about, or the second last, we're going to talk about turning points. Turning points. So what is a turning point? What does it mean? All you have to do is think logically. Where does it turn? Where does it change direction? This would be a turning point. This would be a turning point. This would be a turning point. So they're also called max or minimums. Max or minimum values. So depending on the degree of the function, there are a certain number of turning points, maximum number that you can have. Now sometimes you don't have as many as, well, we'll talk about that a little more, but if, let's say I have a degree of 2, it can only have one turning point. So a degree of 4, like this one here, the maximum number of turning points would be 3. So the number of turning points is always one less than the degree of the function. So we would say a polynomial with degree of n can have up to n minus 1 turning points. Okay, so you should be able to think, well, how do I make it? This is a 4th degree. It had 3 turning points, 2 turning points. You could have, let's do a quick sketch over here. So for 2 turning points, you could have something like this. So it has only this one and this one. So this would be like a triple root and a single root, or you could have y equals x to the fourth, right, which only has one turning point. So fourth degree, for instance, can only have 3 turning points. And finally, that's turning points. Finally, the last thing we need to talk about is the number of zeros. Number of zeros. So the number of zeros, you can have up to n zeros for n degrees, right? N zeros. So, for instance, for this fourth degree function, we had 1, 2, 3, 4 zeros. For a second degree function, this had 1, or if I slid my parabola down, I could have had 2. Okay, so the maximum number is the degree of the function. Now, if you have an odd degree function, odd degree functions. Now, we talked about how the odd degree functions go from quadrant. That way they go from opposite quadrants, right? So odd degree function went from 3 to 1 or from 2 to 4 if it had a negative leading coefficient. So you can see that if you have an odd degree function must have, can you finish the sentence? Must have a minimum of 1, 0. It has to cross the x-axis somewhere. Okay, so you can't go from quadrant 3 to quadrant 1, quadrant 3 to 1 without crossing the x-axis. Now, an even degree function, I'm sure you remember this, may not have any zeros. It just might not have any at all. And why is that? Well, because you know that if you remember when you're doing quadratics, you talked about quadratics that did not cross the x-axis. Or you could have put it down here or something, right? And same thing with a quartic function. I can put a quartic function, I can make this into one like that. It doesn't cross the x-axis. Okay, and finally, the last thing we're going to talk about is symmetry. We talked about that before. Symmetry. So remember we talked about f at negative x was equal to negative f at x. And that was an odd function with symmetry about the origin. So it's odd function, symmetry about the origin. And that was, oops, I ran out of room here. That's like taking your cubic function and spinning it around, right? I could do this, I could turn it around, so it's symmetry about the origin. Same thing with a line, if I flipped it around. And you can have even function. An even function can have symmetry about the y-axis. So if I said g at x was equal to g at negative x, that would be like your parabola, right? If I had a parabola like this, running out of space here on you. So if I had this, so g at negative 2 was 4 and g at 2 was 4, that would be like this. Okay, so that's even function about the y-axis. Now, most polynomials don't have any symmetry at all, because if I move this quadratic away from the origin, it's not going to have symmetry. If I said, what's g at 3, it's not going to be the same as g at negative 3, obviously, right? So, or none at all. And that's most of the time these functions don't have symmetry. Okay, so that's pretty much the basic characteristics. In the next lesson, if you go to the PB Wiki site and download, there's a little practice note there that's going to have some questions that we're going to do together. So you might want to check that out. Bye.
you.